Day 39, reviewing of chapters 4 and 5, and making the nose cone for your rocket. Would you please pause the video for a moment and read through the main ideas from the last lesson, familiar yourselves with the grades for the day and when the next test is, and today's purpose, relevance, and success. Remember, you are allowed one sheet of paper measuring 5.5 by 8.5 inches written on one side. That's basically a half a sheet of paper. If there are outdated messages to students about this sheet being 8.5 by 11 inches written on both sides, please ignore those directions. It's 5.5 by 8.5. It must be handwritten with pencil or pen. No photocopying, no computer printouts. All constants, equations, and facts that would be helpful to you are your responsibility to put on your paper. This paper will be collected and destroyed after the test. Okay, let's review. Find the time for an object to drop 3 meters. So we're going to use the equation that we call the time to drop equation, which is that right there. Let's see if I can get some better light on the subject. That helps a little bit, I think. We'll see. Okay, so the height of the drop is 3 meters. I put that in for the h. Divided by 4.9 equals, and then square root it, 0.78 seconds. Number 2, an object hangs from a string. The string breaks and the object falls for 0.5 seconds. Find the distance it falls. So we're going to use the same equation as before. It's just that this time we're given the time and we're wanting to find the h. So we start off with our equation. Put in the 0.5 for the t. And now I want to get the h by itself. So the first thing I'm going to do is square both sides. 0.5 squared is 0.25. On the right hand side, the square and the square root cancel out. Okay, I want to get the h by itself, so now I multiply by 4.9. 1.225 meters is the h. Number 3, the same object as in number 2 hangs from a string. So in other words, it is falling for 0.5 seconds. And it is falling a distance of 1.22 meters. The string breaks and the object falls for the same 0.5 seconds. Find the final velocity to the nearest tenth. So we know the initial velocity is 0. We know that the time of fall is 0.5 seconds. We know that the acceleration due to gravity is negative 9.8 meters per second squared. And we know that the distance of the fall, h, is 1.2 meters. Okay, now remember that we have the general rule that when we talk about an object falling or being dropped, the initial velocity is 0. Here it hangs from a string, and then the string breaks. And so the initial velocity from that information is also 0. We're assuming that we're on Earth, so it's always negative 9.8. It's in other classes that you might see other planets, or you might see something way up high in the top of a mountain where the acceleration might be 9.7. But for us, it's always negative 9.8. Okay, we want to find the final velocity, so we're looking for v sub f. And that's going to be something in meters per second. Okay, so I'm looking for an equation that has Vf in it, and everything else I know. I may not use all this information. There might be some extraneous stuff there, but we have to be able to put in numbers for all the other parts of the equation. If I go through all my list, I will see that this equation will satisfy my needs. I'm looking for VF. I know VI is 0, I know the A is negative 9.8, and I know the T is 0.5. So let's put that in. Negative 4.9 meters per second will be my answer. Number 4, an object is tossed up at 30 meters per second. What's the acceleration at every second that's in the air? It's always negative 9.8 if it is a free-flying object going through the air. Number 5. Now this counts whether it's going up or going down or at the very tippy top. Gravity is always the same strength as long as you're throwing stuff around into the surface of the Earth. So it's always 9.8. Gravity is always pulling downwards, which is the negative direction. So the acceleration is always negative. It doesn't matter which way the velocity is, the acceleration is always negative. Number 5. An object is tossed up at 30. What's the velocity at the very tippy top? For one mere instant, it's at 0. Please remember, it's not hovering there for a millisecond or a microsecond or a nanosecond or whatever small fraction of a second you want. It is not a length of time that it's 0. It's a mere instant, just one spot of time. It's really hard for us to understand a spot of time, but it's sort of like a spot in geometry. In geometry, when you plot a point on a graph, it supposedly has no width or length or height. The dot of our pencil or pen will, but that represents this imaginary thing that has no width and no height. Anyway, let's go on. Number 6. An object is tossed up at 30. What's the velocity as it hits the ground? The velocity is going to be the same digits, 30, but going in the opposite direction. It's falling downwards when it hits the ground, so it's going to be a negative 30, and then we have our meters per second. Number 7, an object is tossed up at 30. How long is it in the air? Okay, so let's write down what we know. The initial velocity is a positive 30 meters per second. We know that the final velocity is a negative 30 meters per second. We know that the acceleration of gravity during this whole time is negative 9.8 meters per second squared. That's all that we know. The signs are all taken care of, units are compatible. What we're looking for is the time, and that's going to be so many seconds. So, what equation will work? You can look at all of them. You're trying to find an equation with t. And it's going to be the same one as up here. VF equals VI plus AT. We're looking for the t, so that stays a letter. The acceleration is negative 9.8. The VI is positive 30. And the VF is negative 30. First step is to subtract off 30 from both sides. And then I'm going to divide both sides by 9.8. 6.1. Oh, I got crazy units there. I was thinking it's acceleration. Nope. This is merely time. So it's just seconds. Oh, what an ugly mess. Okay, there we go. Let's put a little seconds there. There we go. Now we're official. Number 8. A marble rolls off a countertop that is 0.9 meters above the ground. The marble is rolling at 0.5 meters per second. What is the range to the nearest tenth? The first step is to find out how long the marble is in the air. And the marble is going to be in the air no matter how it's moving horizontally. It's going to be in the air according to how high it is. So just as if we just simply drop the marble off the countertop, we're going to use the time to drop equation. We're trying to find the time. The height is 0.9. Don't forget to take the square root. So the time is 0.43 seconds. Okay, then we find the range using this equation. Range is the average velocity times time. We're looking for the displacement, the horizontal displacement. The average velocity was 0.5. And the time we just figured out to be 0.43. And I get a range of about 0.215 meters. Forces. An object is pushed to the right with a force of 50. At the same time, it's pushed to the left with a force of 30. Find the net force to the nearest whole number. So to the right with 50, and I'm going to draw the other vector arrow being head to tail. So I start here and I go backwards to the left 30, and the answer is going to be from the beginning of my train to the end, and I can see that I'll need to subtract 50 minus 30 is 20. So 20 to the left. Number 2, an object is pushed to the right with a force of 50. At the same time, it's pulled down with a force of 30. Find the net force. So to the right with 50, and then down 30. Notice I make the arrows proportional to the numbers. So the 50 is longer than the 30, and then the answer is from the beginning to the end of the train, so to speak. And I'm looking for that side, which we'll call C. So I can use Pythagorean theorem. A squared plus b squared equals c squared. 50 squared plus 30 squared equals c squared. 2500 plus 900 equals c squared. 3400 is equal to c squared. Take the square root of 3400. And I get 58.3. Number 3. An 8 kilogram object is accelerated at 4 meters per second squared. Find the net force. This is a mass. That is an acceleration. We are looking for the force. So we should use the equation F equals ma. Newton's second law. We're looking for the force, so that stays a letter. The m is 8. The a is 4. So we get the answer of 32 newtons. Number 4, an 8 kilogram object is pushed with a 33 Newton force. Find the acceleration. So that's the m, the 33 is the f. We want to find the a. So f equals ma, f is 33, m is 8. We're looking for the a. 33 divided by 8 is 4.12. Let's just call it 4.1. And that's going to be meters per second squared. An 8 kilogram object is not moving. What is the net force? Remember Newton's first law. If there is no net force, then there's no acceleration, and vice versa. If there is no acceleration, there is no net force. So it's not moving, so therefore it's not accelerating. So therefore the net force is 0. Number 6. An 8 kilogram object is moving at a steady 3 meters per second. What's the net force? If it's moving at a steady 3 meters per second, that means that the acceleration is 0. So therefore the net force is 0. If I used F equals ma and I put 0 in for the acceleration, it doesn't matter how big or small the m is, 0 times anything is going to be 0 force. Number 7, a car pushes on a tree. This is the action, car pushing tree. The reaction, or we could say counterforce, Either way. The modern version is counterforce. Newton's ancient version is reaction. Okay, the reaction or counterforce is a tree pushing on the car. I use the same verbs and nouns as over here. I just flippy-floppy them. I move the car to the end and the tree to the front, and the verb is in the middle still. Number 8, the bat hits the ball. The bat pushing on the ball is the action. The reaction, according to Newton, is the ball pushing on the bat. And that causes the bat to slow down a tiny, tiny bit, causes the bat to vibrate, causes the bat to make a sound. Number 9, in a suspension bridge, the cables experience forces of tension, and the towers experience forces of compression. In a stone arch bridge, the stones experience forces of compression. 4 basic forces of nature are gravity, the strong force that holds the protons together in the nucleus when the positive protons want to repel each other away. There is a weak force that works inside subatomic particles. It's related to the changing activity of neutrons and protons, and that's pretty much all that I've said about it, and that's all that you need to know about it. And then we have electromagnetism. They used to think that the forces of electricity and the forces of magnetism were completely separate, different things. But they've discovered that they're actually 2 sides of the same coin, and so they threw them together to call them electromagnetic forces. Shear. That is when we have 2 opposing forces on opposite ends of an object, and so you end up stretching it like that. So when you rub your pencil eraser on a piece of paper, that is shear. Torsion is a twisting. So when you twist off the bottle cap of a soda bottle, that is torsion. In another video, I will show you how to do the nose cone.